Hello and welcome to this video titled Identifying the Network Bits. In this video we're going to cover IPv4 address classes. We're going to determine how to figure out what class an address belongs to. And I'm going to introduce to you the concept of an IPv4 subnet mask and what it is and why we need it. And then we'll finish up with IPv4 address types. So let's start by looking at IPv4 address classes. Now, if you've studied IPv4, you know that one of the critical components of the IPv4 header is the address. There's a destination address of where a packet's going and a source address of where a packet's coming from. And you also know that when a device like your laptop or tablet creates a packet, it puts its own address in there as a source, and it puts in the destination of wherever it's trying to reach, like INE.com's destination IP address or Google's destination IP address. But before that packet can get going, the next thing that has to happen is that device has to do a comparison of those two addresses. And it has to say, okay, is the destination I'm trying to reach in the same network as me, because that will influence how I transmit this packet, or is the destination I'm trying to reach not in the same network as me? Well, here's the kicker. Those two addresses are just 32-bit binary numbers. There's a 32-bit binary number for the destination, a 32-bit binary number for the source. So how does it answer that question? Well, the way it does that is because it looks at its source address. And the device, when it looks at its source address, it has to know somehow of those 32 bits that there's some bits in the beginning that form a common pattern for everybody that is on its own local network. In other words, if I'm sitting in the payroll department, and let's say that the IP address I've been given in binary looks like this. I'm not going to do 32 bits, but let's just put some random bits in here. My laptop somehow has to know that this right here is a binary pattern that's common to everybody else in the payroll department. That's my department. So if I create a packet and the destination of the packet matches this exact same pattern, I know that destination's in my network. If the destination of the packet has some pattern different than this, then I know it's not in my network and I have to forward that packet to a router. So now we have to answer the question, if this is the number I have, how do I know where this dividing line is between my networking bits, which tell me what group or department I'm a part of, and my host bits? How do I know where that is? Well, let's start with the way the old timers did it, and then we'll go into the way we've done it for the last couple of decades. So originally, when IPv4 was first invented way back in RFC 791, we're talking about the really early 1980s here. The developers of IPv4, they said, hey, IPv4 is going to have an address. The address is going to be subdividable via a network portion and a host portion. Okay, how is a device going to know where that dividing line is? The original developers of IPv4, they said, okay, here's what we're going to do. We're going to divide addresses into what's called classes. And depending on what class an address is in, will automatically tell you where that dividing line is. Now, how does a device know? So we're talking about like 40 years ago here, well, 30, 40 years ago. How does a device know what class of address it has? Well, it was based on the very first few bits in binary. So remember, computers look at this address as just a 32-bit binary number. So back in the old days, they would look at the first few bits, so if we read it from like left to right, the first few bits, and just the bit pattern alone would tell it what class of address it was. And now that it knew what class of address it was, it would be able to distinguish where the networking bits ended and where the host bits began. Okay, so how did that happen? Well, so let's take a look at those patterns. So the first class of address is called a Class A address. Any IP address that in binary starts with a 0, if that's the very first binary bit from left to right, we're done. That is a Class A address. And according to these rules way back decades ago, a Class A address said, hey, your networking bits are the first 8 bits, the first byte. That's your network. Now, what if it wasn't a 0? Well, then we had to keep moving on. Then we looked at, if it was a 1, then we looked at the next bit. If the next bit was a 0, so now if we had a 1, 0, we're done. That's a Class B address. And using classful addressing, that meant that the first half of your address was the networking bits. That's the department you're on now. That's the common pattern that you and everybody else in your network share, is the first half. Now, if the pattern was a 110, that was a Class C address. And you can probably guess where this is going. Now the first 3 octets denoted your network. Now there were 2 other address types as well, and I'm going to show you those here in just 1 second. They are on this slide, but I want to preface it by saying that when it came to assigning IP addresses to hosts, like laptops, PCs, servers, router interfaces, all the addresses you can assign to a particular host are going to fall in one of these 3 ranges here, A, B, or C. So the next 2 ranges I'm going to finish up with on this slide are not used for addressing hosts. In other words, a NIC card on a laptop or server or smartphone will never have an address that is in the next 2 categories. So what are those 2 categories? Well, you can probably figure out what the bit pattern is going to be next. 1110. That is a Class D address. That is reserved for something special that we'll talk about towards the end of this video, which is called multicasting. So whenever an application is doing multicasting, if somebody says, hey, I'm doing IPv4 multicasting, right there, you know, oh, the destination address, the destination, this is only used for destinations, not sources. The destination of that packet would be something in binary beginning with 1110. And then Class E, that was experimental. That was never actually implemented, that was never used. As a matter of fact, if you go onto pretty much any operating system, whether it be Windows, Mac OS, whatever, and you try manually giving it, statically typing in an IP address that's in the Class E range, you'll get an error message. Every single operating system knows that that is untouchable, that is experimental, and that was never opened up for use. So that's just a waste of space. Okay, well, this worked for the first handful of years of the life of IPv4. But it didn't take too long after IPv4 was originally invented that the developers of it said, wow, this is really catching on like wildfire. I mean, networks are sprouting up all over the place. It's getting crazy out there, and this way of doing the address of determining where the network and the host bits are isn't going to work for too much longer, because there's only a certain finite number of networks available in Class A, Class B, and Class C space, and they were running out pretty fast. So they said, okay, we need to come up with something different. Classful networks, not scalable. So we need to have some other way of just arbitrarily setting that line. Why can't we have the line between where the network bits end and the host bits begin? Why can't we have that after the first 9 bits, or the first 12 bits, or maybe the first 21 bits? We should give the people the ability to arbitrarily set that dividing line between where the network bits end and where the host bits begin. And this is where this concept of a subnet mask was introduced. So this was introduced way back in 1985. If you want to read the original RFC for it online, you can Google RFC 950. And then a few years later, okay, so we're talking about 8 years later, this thing called classless interdomain routing, sometimes called CEDR, was introduced in 1993, and that's when classful addressing was formally deprecated. They said, okay, from this point on, nobody should do classful addressing anymore. At this point, everybody needs to use subnet masks. All right, well, what the heck is a subnet mask, and how does it replace classful addressing? Well, here's how it works. So here's your IP address. Here's your 32-bit number as your computer sees it. Now, if this was a classful address, if we were talking about 1980 or something, the computer would say, oh, okay, I see right here, the first bit is a 0. So that tells me this is a Class A address, which tells me that the first 8 bits are my network, so that's my pattern. Okay, but we're not doing that anymore. So if he can't use a class, what can he use? Well, here's the thing. Every device that runs IP for the last couple of decades, when it learns or is given an IP address, you have to also give it a subnet mask, which is another binary number. But it's a comparison tool. The subnet mask is compared directly against the IP address, and this helps the device that has the IP address answer that question about where the network bits end and where the host bits begin. And it's a real simple comparison. So in any subnet mask you see, it'll start out with some continuous or contiguous section of ones, and at some point those 1 bits will end, and now you'll have contiguous zeros all the way to the end. So basically what you're going to do is you're going to pay it, or your computer would look at those 1 bits, and they would say, okay, going left to right, how many 1 bits do I have? Okay, in this case I think I've drawn out like 12 1 bits or something like that. So now it's going to go to its IP address and say, okay, if the first 12 bits of my subnet mask were 1s, and I didn't count that up, but I think it's 12 bits, then that means the first 12 bits of my IP address is my network. That's where the dividing line is. So you can see here, now we've identified our networking bits because we just basically layered the subnet mask on top of the IP address, and it's a 1-for-1 comparison. Hey, if that subnet mask only had the very first 2 bits set as 1s, 1, 1, and then 0, 0, 0, 0, then that would mean that in my IP address, only the first 2 bits belong to my group. Only the first 2 bits were my network. Now you're not ever going to see that, but that's how the logic of the subnet mask works. So we're no longer, so this is classless interdomain routing. We're no longer looking at the class of an address. Class is irrelevant now. Now every IP address has to come bundled with a subnet mask. And the subnet mask tells you where those networking bits end and where the host bits begin. Okay, so let's talk about different types of IP addresses. So some IP addresses, most IP addresses, are what we call unicast addresses. And these are used for one-to-one communication. So these utilize addresses in the class A, B, and C space. You say, wait a second, Keith, you just told me we're not supposed to think about A, B, and C anymore. All right, let's talk about that. Because a lot of people come to me and they say, hey, I understand that classful addressing is a thing of the dinosaurs. That's been dead for decades, probably since before I was even born in some cases. So why do I even have to learn about it in the first place? Well, there's a variety of reasons. Number one, if I told you, hey, go onto your laptop and give it this IP address, 225.7.7.10. All right, so trusting me, you go to your laptop and you try to put that on and you get an error. You come back all frustrated with half of your hair pulled out and you say, Keith, I kept trying to put that IP address on there and I kept getting an error message. What the heck is going on? Well, if you didn't know about classful addresses, you wouldn't know that this address here is in the class D space. Because in binary, the number 225 begins with 1110. So that first octet looks like that. Well, guess what? Class D addresses, you can't put those on devices. That's used for multicast. That's used for a special application. Well, if you didn't know what Class D was, how would you know that? You wouldn't. Another practical example. As you get further into the world of networking, you're going to learn something, and especially once you start getting into the world of routing and how routers do their thing, you'll learn something about route summarization. Now, if what I'm about to say here goes completely over your head, don't worry about it. It will make sense in a few weeks or months when you get to the topic of routing. But let's say here that we have a router. Let's just call him router A. Okay, and he's connected to router B. Now, router A is learning about a whole bunch of networks. Maybe he's learning about the 10.10.10.0 network. oops. He's learning about 10.10.5.32 network. And don't worry if you don't understand this nomenclature that I'm writing down right here. 10.10.100.0. Okay? Now, the normal behavior of a routing protocol is that whatever routes he learns, he just sends those routes on to his neighbor. So he keeps a copy for himself so he knows where they are, and he sends it on to his neighbor. But in this case, we could say, oh, wait a second. Router A, isn't every single route you're learning have something in common? Don't they all begin with 10? So on this interface, as an example, we could turn on something called route summarization, which basically gives the router the permission to just send out one route that sort of collapses or contains all of these. Now, here's the thing about route summarization. In every single routing protocol, well, not every routing protocol, but most routing protocols, you have two ways to do it. You have something called auto summarization, and you have something called manual summarization. Manual summarization means you as the human being have to take a look at all these networks and you have to ask yourself, what do they all have in common? Well, looking at this, I can pretty clearly see that all these networks start with 1010. So if I was doing manual summarization, I would send this network over to router B. Say, hey, router B, anytime you get a packet where the first 16 bits, so if a packet's coming in here or here or here, if the first 16 bits of that destination match this pattern, send it over to me, router A. I know how to get it there. So with manual summarization, it's like CEDAR that we just learned about. With manual summarization, you get to choose where you want that dividing line between network and host. In this case, you'd say, all right, I've got all these networks I've learned about. What do they all have in common? All right, that's where my dividing line is. I'll advertise one network to you that collapses them all together. But if you're running auto summarization, most routing protocols, when you turn auto summarization, what do? They shrink everything back to its classful boundary. Now, if you didn't know what network classes were, you would have no idea that 10 is a class A address. It's in the class A range. And now that you know it's in class A, you know that class A networks, the first byte was the network, the remaining bytes were host. So in auto summarization, he's not going to send 1010, he's just going to send 10.0.0.0. If you didn't know anything about classful addresses, you wouldn't understand why auto summarization did something like that. So, like I said, that might be above and beyond what you know at this point, but hopefully it gives you a little bit of a clue as to, yes, Charlie Brown, there is a reason still to this day to know something about classful IP addresses. All right, so unicast. You got a PC right here. He wants to talk to a server right here. Maybe they're separated by a router, so they're in two different networks. So that means that this guy's going to have some source address. This is going to be the destination address because it's going to go this way. So unicast means one-to-one. This one laptop is sending a packet to this one destination server. Whatever his source address is going to be something in the class A, B, or C space. We don't know what it is, but it's going to be in that range somewhere. And the destination, whatever his IP address is, will be in the class A, B, or C space. Now we also have multicast. This is one-to-many communication and utilizes class D address space. What this is referring to is, let's say that there's a server over here. Now he's going to have some source address, which is in the unicast space. So let's say he's 1.1.1.1. All right, that's his IP address. Kind of sloppy writing right there, but you get the idea. 1111. And let's say on this network segment, let's say these squares here represent some PCs. Oh, Keith, you're so old. Nobody has PCs anymore. That's okay. Don't give me a hard time. All right, so here we have some PCs. They're very politically correct PCs. All right, and each one of these guys has some IP address. Let's just say, let's just make some stuff up here. Actually, it doesn't really matter what their IP address is. That's irrelevant. I'm just going to put some letters here, A, B, C, D, and E. All right. Now, this guy, this server, he's putting a video on this wire right here. Maybe, as a matter of fact, it's a video that goes out 24/7. Maybe it's a feed from a camera. Oh, let's make it something more interesting than that. Maybe it's the news. All right, 24/7 newscast, news all the time. Get your pessimism here. I'm sorry, I shouldn't have said that. Anyway, the video's going out 24/7, and here's the deal. If, let's say, PC A and PC E wanted to get that, what if they want to watch that? Well, if we sent this out as unicast, we'd have to have a stream of video going directly to PC A's IP address, whatever it is, and a copy of that stream going to PC E's IP address. Not a big deal until we start having hundreds or thousands of people that want to watch that video. If I've got hundreds of people that want to watch that video feed, this server is going to have a real hard time creating hundreds of copies of these packets going to all these different hundreds of addresses. That's not going to scale very well. All right, well, what other alternative we have? Well, we also have something, I actually probably should have had it before multicast, but it's going to come up here in the slide, which is called broadcast. A broadcast packet is a packet that once it goes out, everybody has to listen to it. They don't have a choice. Everybody has to listen to that packet no matter who they are. Well, that's not really ideal in this situation either. I mean, it's helpful on the server. All he has to do is send out a single stream of packets, but if the destination address of those packets was broadcast, that means that all these PCs would have to interrupt what they're doing to watch that broadcast. And PCs B, C, and D, they don't care about the news. They're not watching that right now. So broadcast not too useful. So this is where we could use the concept of a multicast. So here's how multicast works. As the slide shows, multicast addresses are only formed in the source. So if here's my packet, not the source, the destination, the source address will be a unicast address. The source address will be the address of whatever server is pumping out this multicast video or audio or whatever it is. It's the destination address that will be special. The destination address will be a multicast address. And because it's class D, that means it's going to be somewhere from 224.0.0.1, that is the smallest class D address you can have, up to 239.255.255.255. That is the largest class D address space. So this right here is all class D, and a multicast is going to go to that. Well, how's that going to help these guys down here? Well, let's say this video here, let's say the person who created this video stream on the server, he decided that he wanted the destination to go out to 227.777. Here's the way this would work. Now, each one of these PCs, remember, they've got their own unique address. Maybe this guy is 1.1.1.2. Maybe this guy here is 4.4.4.4. You know, who knows what they are? 7.7.7.7. Okay? So, the guy on PC A, he decides that he wants to take a break and watch the multicast news stream. So what does he do? He sends a unicast packet to some directory server somewhere. I'll just say DS. Maybe he is 8888. So somehow all these PCs have to know in advance that there's a directory server out there at 8888, and you go to him to find out what the shows are. It's kind of like, you know, if you have DirecTV and you pull up the guide, and the guide will show you, okay, go to this channel if you want to watch this show. Go to this channel if you want to watch this other show. Same type of thing. This guy is the guide. So we send a unicast packet to him. So PC A, who is at 1112, would send out a unicast packet going to 8888 and say, hey, what shows are available right now? This guy would send a unicast packet back saying, hey, if you want to watch the news, that's currently going out to 227.777. 7.7.7. So now what PCA does is his NIC card is reprogrammed. Right now his NIC card, is his network interface card, is really only looking for packets going to 1112. That's all he cares about. Now we say, hey NIC card, in addition to 1112, if you ever see a packet going to 227.7.7.7, I want to see that too. Pick it up, send it to my processor. So right now there's a stream of packets going onto this wire going to 227.7.7.7. PCs B, C, D, and E are ignoring it because that's not their address. But now PCA can pick it up and watch it. Now maybe a few minutes later, PCE says, you know what? I'd like to watch the news as well. He does the same thing. He sends a packet to the directory server. He finds out that the news is going to 227.777. So maybe his original address was 1.1.1.5, but now he programs his NIC card to also listen to 227.777. And now he can get a copy of that packet as well. This is why we call multicast one-to-many, because it's coming from one multicast source, but any number of arbitrary destinations can view and pick up this packet. They just have to know in advance what the multicast destination address is. Once they know that, they can program their NIC card to listen to that. And then once they're done, if PCA says, okay, I'm done watching the news, time for me to get back to work, he can shut down his multicast application, and now he's no longer listening to 227.777. So even though those packets might still be going onto his wire, he's no longer going to pick them up and watch them. So that's how multicast works, and the destination is always in this special reserved range here of class D. And then the last thing, which I briefly mentioned, is broadcast. This is one-to-all communications, and there are two flavors of broadcast. There's general broadcasts and directed broadcasts. First of all, let's start talking about the general broadcast, because that's probably the one you're going to see the most often. Anytime you see a packet with a destination address that matches this pattern right here, that is a general broadcast. That means, hey, everybody, everywhere, you have to pay attention to this. A common use of this would be, for example, whenever your laptop or PC connects to a new network, like let's say you pick it up, carry it under your arm, walk over to a conference room in the next building, plug it into the network there. Well, now your laptop's going to say, oh, I just got plugged into a new network. My network interface card is receiving energy. I'm on a new network. First thing your laptop's going to do is he's going to say, I need an IP address that's appropriate for the network I'm sitting on right now. So your laptop is going to send out a special message called DHCP, the Dynamic Host Configuration Protocol. Your laptop's going to say, hey, is there a DHCP server out there somewhere that can give me an address that's appropriate for where I am right now? Well, your laptop has no idea if a DHCP server exists that can give you that information, or if he does exist, where he is. So this is where broadcast would be used. Your DHCP packet that you send out, the destination address would be this pattern right here, which is saying, hey, everybody everywhere, you need to stop what you're doing and look at this, because I might be talking to you. Now, directed broadcast, you're not going to see that as often. That would be something like this. Let's say that you already knew what your IP address was, all right? Let's say your IP address was this. Now we know that that's your IP address. You got to know what your networking bits are and what your host bits are. And how do you do that? With the subnet mask. So let's say the subnet mask looked like this. Now remember, the way that your laptop or PC views the subnet mask is in binary. So this here translates to 11111111, 11111111, and then a whole string of zeros. That's what this value stands for. So that means when you compare it against your IP address that your network is the 1.1 network. Me as a host, I am 1.1 as a host, but there might be somebody else on my exact same network who is 1.1.55.9. and somebody else who's 1.1.32.7. As long as we all begin with 1.1, we know based on our subnet mask that we're on the same network. Now, what if I want to send out a broadcast, but here's the catch. I don't want to send it to necessarily everybody in the world on every single network. I just want to direct it to people on my network. This is what's called a directed broadcast, a broadcast that says, hey, this broadcast is only meant for people in this network. Well, here's how I would do it. If my network is 1.1, I would set my host bits to 1s. So remember, here's how your computer sees your IP address. 1, 2, 3, 4, 5, 6, 7, 8. There's my first byte, which is 1. 1, 2, 3, 4, 5, 6, 7, 8. All right, and then after that it says everything, so it says that is my networking bits based on my mask, and everything else after that are host bits. Well, in a directed broadcast, you keep the networking bits to whatever they are, but you set your host bits to all 1s, which in this case would translate to 255.255. So this would be a directed broadcast. Everybody in the 1.1 network would have to get it because it's not going to any particular host. No host will ever have the host bits set to all 1s. That's illegal. So when you look at your host bits here, if your host bits are all 0s, or if they're all 1s, that means something special. That is not a host. Any IP address where the host bits are all 0s or all 1s, that will never be assigned to any laptop, server, PC, whatever. In this particular case, if they're all 1s, that is the directed broadcast. So that concludes this video on IP addresses and how to differentiate the network bits from the host bits. Thank you so much for watching.